All right, guys. So in the last section, we talked about limits, and this section, what we're going to do is talk about limits that instead of approaching a finite number like 5 or -3, they approach infinity or negative infinity. We'll start by looking at graphically what that means, how to use the properties of limits when we have limits that involve infinity, and then in the next class we'll talk about some usefulness of it. Why would we use it? So what I want to talk about first is the idea of infinity. What is infinity? So the first thing for you guys to keep in mind is infinity is not a number. So when we start working on problems and we say, oh, the answer is infinity, or oh, the answer is negative infinity, what we're doing is we're not communicating a numeric answer. We're communicating an idea. And the idea is this. Let's say that we want to understand what x approaches infinity means. So when we write something x and then the arrow and infinity, what we're saying is x approaches infinity. And what that means is if we imagine a number line with the positive and negative x-axis, x approaching infinity means that we are considering values of x that are getting larger and larger and larger. We're not considering a specific value. We're considering what happens to a function or what happens to a variable as we look very, very far to the right on the x-axis to extremely large numbers. And the idea of infinity would be a number that is, at the end of that axis somehow. It's bigger than any other number. So think of it as going very, very far along the x-axis. Or if we had, say, x approaches negative infinity, then we would be moving this way. So if we were to say something like as x approaches negative infinity, then we're moving very far along the x-axis and considering extremely large numbers along the negative x-axis. So let's look at this function. This function is 1 over x, and the graph looks like this. Now this window is only graphed from -4 to 4 because this function has what we would call end behavior that approaches very quickly. You guys might remember from last year that this would be considered a horizontal asymptote. The function is approaching 0 as we get large on the positive or negative x-axis. The way that we would actually write this with calculus is we would say as x approaches infinity, 1 over x approaches 0. Notice we don't use an equal sign. We use an arrow that means the word approaches. So as x approaches infinity, meaning as x gets very large, the function takes on a value that's very small. The function's value being, the vertical axis. This is x, and this is f of x. Same thing over on the other side. Here we could write as x approaches negative infinity, the function 1 over x approaches 0. We've got another asymptote. We have a vertical asymptote at 0. So we could also write as, now this one's a little bit more complicated because we can't just write as x approaches 0, the function approaches positive infinity. And the reason we can is because when we approach from this side, we go up to very large values along the y-axis. So that would be moving towards infinity, very large, big values. But if we approach from this side, we're approaching very large negative values along the y-axis. So this is where handed limits come into play. So what we would say here is as x approaches 0 from the right, the function approaches infinity. And down here, we would say as x approaches 0 from the left, the function approaches negative infinity. Okay? Putting this into terms of limits, then we would have what we've got here. So actually, let me just write it out. So putting these two together, we could write the limit as x approaches infinity of the function 1 over x is equal to 0. And then over here, what we could write would be, oh man, the limit as x approaches negative infinity of the function 1 over x is equal to 0. And we could actually put that all together if we've got a limit from the left, or a limit approaching positive and negative infinity, and the limits are the same. We could put those two together and write it like this. So if we have the limit as x approaches infinity of f of x is equal to b, and the limit as x approaches negative infinity is equal to b, then what we could write is we could write the limit as x approaches positive or negative infinity of f of x is equal to b. So this is a special shorthand that we're allowed to use for limits that involve positive and negative infinity, and only if the limits are the same, like this case. So that would be the situation where our horizontal asymptote is the same in both scenarios. Now, here in yellow, we can't put these limits together. Here, this would be the limit as x approaches 0 from the right of f of x is equal to infinity. And unfortunately, remember that for a limit to exist, both handed limits have to approach the same value. So in this case, this doesn't work. So we've got the limit as x approaches 0 from the left of f of x is equal to negative infinity. Since these two limits don't match each other, we cannot write the limit as x approaches 0 of f of x equals something, right? Because it's approaching two different things depending on which side we approach 0 from. So the limit itself does not exist. So we would write does not exist because these two limits, the left and right-handed limits, don't match. If we're asked specifically, we would need to just list the left and the right-handed limits. So let's take a look at this graph, and we're looking for horizontal asymptotes. So that means we're looking for the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. And we want to get used to trying to use our calculator to figure that out. So I'm going to put the graph in. Okay. And let's go to standard, and we'll see where we're at first. So my window right now is going from -10 to 10 on the x and the y-axis, and it looks like we're getting a pretty good idea of what this limit is. We can use the trace function to move the cursor really far out and see how the y value is behaving. And in this case, we can see that that y value, it appears to be approaching 1. So let me show you a couple different techniques that we can use to verify this. So the first one was just using the trace feature, and we could extend the window if we need to get farther out just to verify. We can also go to the table and look and just kind of keep moving out on the table. We might want to go table set, start our table. Let's start our table at 0, but let's move by tens so we can make a lot of progress. It'll be different for each graph, so we might want to move by tens or hundreds. But look at how closely we're getting to the value 1 on that side. Or if we go to the negatives, we're going to start really approaching -1 there. So it looks like our horizontal asymptote on the right side, or the limit as x approaches infinity, is 1, and the limit as x approaches negative infinity is -1. So we can see those asymptotes there. Right? So we're not always going to have our calculator on the test. There's a couple of sections on the test where you don't have your calculator. So we are going to also talk about ways to solve these limits without the use of a calculator. So let's move on to example 2. Here's an example where we're not going to be able to take this limit just by evaluating it. And the problem is this. The top function is sine of x. And we know that the graph of sine of x just kind of looks like this. Right? It just varies between 1 and -1. So it doesn't have like a horizontal asymptote or anything like that. And then we're dividing by x, which is just getting larger and larger and larger. This is another example where the sandwich theorem will help us. So let's go through that. So like we were just saying, sine of x has a range where it's basically always between 1 or equal to 1 and -1. It can't ever, extend past that. That's its range. Now, if we wanted to instead make this inequality look like the function we were given, we could multiply everything by 1 over x. So we would have -1 over x, 1 over x times sine of x, and 1 over x. This is usually how you prepare for the sandwich theorem. And really what we're saying is, because sine is basically just a number between -1 and 1, it's either going to leave the function alone, multiply by -1, multiply by 1, or scale it down to be something smaller that lies in between those two answers. So then what we can do is we can take the limit as x approaches infinity of -1 over x, see what that's equal to.